I want to thank the organizers, which is GMLC, for is not here. I will thank him later. For inviting me here. I was first hesitant, and then I suggested a couple of topics. Then she now picked this one, which is not quantum. And then I thought I should try doing it because when I think, we go around giving talks all over the world. Last time I gave a presentation at Rice was 2009. So it was my field request. It wasn't my birthday. 2009, and I think that's a shame. Okay, so anyway, but it's hard. It's unusual talk because I never gave it before, which means I have to make slides from script. Thank you very much. It's also, you will see that it's not quantum, but all materials are quantum. And of course, now what we say quantum, we mean more advanced exotic properties, correlated systems, unusual superconductivity, flat bands of correlated systems, whatnot, chiral behaviors and materials, strong spin Rashba effects of spintronics, zero things. And as this quest expands, of course, we encounter more and more really material platforms, and some of them are different, some of them have low symmetry, and in some cases, you bump into a problem which kind of seems like 100 years old problem, and it's not solved because you bump into special situations with your material. So this is this type of situation I want to describe. And you know, Rice Campus, I don't need to discuss this slide. This is my group, pretty much. It's outdated picture, but roughly there are 4 people who are involved in this particular project. And this will be only one paper for pretty much presentation with some background. What we do in my group, I'm in material science and I'm in engineering department. Although I'm a physicist by background. What we do in my group, we try to understand how to go from interatomic forces, describe the different levels of precision, from quantum to classical empirical potentials, whatnot, molecular dynamics, Monte Carlo simulation. Basically, from here, using computers, how to explain or predict why different situations with different elements assemble in different forms and shapes. And this was very big kind of area. And sometimes we work on quantum behaviors, but pretty much we work on materials, trying to understand what's going on. Now, so we kind of use, of course, applied quantum mechanics and quantum chemistry to solve reasonably applied problems, mostly from chemistry, material science, or physics. And sometimes, not long ago, I bumped into this company. I thought it represents well what my group is doing. I was going to buy this truck, but they refused to sell it, so I only have a picture. But I think it's good. I know this company, people, yeah, it's in Texas somewhere. Okay, so that's what we do. So the team on this project is also unusual, because the project was so long, it was kind of on the back burner. It's kind of very extensive and difficult when it comes to computing real materials and because large volume. Although it's not the focus of results of presentations. And these people are all moved out. So Luqing Wang, who is actually was a wonderful student, and she is the main worker on this project. She is now in Argonne Lab and looking for faculty position now. Zhuhe Zheng went back to China, where he is a professor, maybe associate dean or something in Nanjing. And Sharmila just recently joined as editor of some kind, editor of physical letters in Washington. She didn't know. Okay, so that's the team. And myself, of course, I was dragging it for a long time. So what is it about? This is about crystals. Crystals for all of us kind of simple people, jewelry, solid material, sculptures. It's about colors and shapes mostly. Of course, there are different properties, many, but mostly colors and shapes. And some shapes are manufactured, some shapes are just randomly broken, and some shapes are equilibrium. An equilibrium shape is a fundamental thing because it's well defined, provided the chemical composition of your material. There is one equilibrium shape which can be found somehow or exists at least in nature. Okay. In case of liquids, it's pretty obvious because they obviously minimize energy, it's pretty much surface energy, and it becomes spherical very quickly because they're fluid. In case of materials, not so fast. It's a trial and error experiment which can go on geological times, and we cannot do it. We also cannot do it in physics. This kind of topic, which is particularly came to fore kind of when we moved to two-dimensional materials recently. Why? Two-dimensional materials are flat, so all the shapes become much more visible, much more factual kind of. It's difficult to analyze shape of three-dimensional object, and microscopy of course advanced. If I give it a big kind of time stroke, like this 100 years kind of things about shapes of materials. So I just give you a couple of examples. This is simple. This is graphene, which forms these nice hexagons according to its symmetry. This is growth of graphene. Don't pay attention, it looks good. This is a whole family of TMDs, which I collaborated, we discovered, they did all the work experimentally in a Singapore group. They all show interesting shapes, and you never know if they're equilibrium or they're kinetically limited, or they may be just fractured and broken into some bad shape. We don't know. But this is interesting. It brings into question, what are equilibrium shapes for all this stuff? Equilibrium shapes, of course, is a classic thing. It goes back to Gibbs. Maybe even before Gibbs, people thought about it. Gibbs first kind of realized that it's difficult to minimize three-dimensional volume. Volume and size are pretty much the same. So what you need to do, you need to minimize surface. So it's a surface functional. It should be minimized to find ground state, to find minimum. Either free energy or Gibbs potential or just energy, because temperature, entropy, and pressure and entropy do not play much role. So, but this was just kind of theoretical advance. Practically, it was done by Wolf and without any proof. He just from many observations, he came to this thing, Wolf construction, or Wolf theorem, which became a tenet of crystal physics and stays the tenet of crystal physics for more than 100 years now. This was about, even though that work, but not mine. 1900, Wolf classic paper, which was originally in Russian and no proof, but this is correct. So only Max von Laue, much later, as you see, 40 years later, provided proof of this. And theorem is simple, or construction. It's actually a recipe, you can say. Minimum energy is for a given volume is achieved if all distances from some point are simply proportional to energy of appropriate kind of direction, with appropriate phase. And then he called it capillary constants. So this is all fine. If you have gold, you have crystal lattice, for example, gold, you can, if you know different phases energy, you can construct this whole thing, and then you know atomic cluster. Atomic cluster will be a little bit actually chopped at the corners. This is not precise picture, it doesn't matter. So it works. And if you look, you can, if you never looked before, there are thousands and thousands of papers using this full construction and beautiful images and beautiful videos showing how this thing kind of happens. Then you draw all these tangent lines, and then you have envelope, which is predicted shape of a crystal. This is all good. This is all good. Problem is that, yeah, you need to know surface energy. You need to know surface energy. And when you look at some cases, in some cases, you realize it is difficult. To me, it happened long ago. Long ago, we were working on normal, classical, important semiconductor, silicon carbide, gallium arsenide, gallium nitride word and we wanted to use density functional theory, which at that time was not as established and popular users. Now, we thought that we can calculate surface energy. We can determine absolute values, which is fundamental thing, right? Sometimes it works. DFT or whatever method is not enough because you need to start from something. You only can calculate total energy is the only thing you can define and calculate. So what you usually do, you take a slab of material, like this phone, but this phone is better now. This one. And you calculate energy of this slab, and then subtract bulk, and then divide by 2. Divide by 2 is important. Then you get energy of each surface. Okay, that's easy. Problem is in some cases you don't have inversion symmetry, and then like this one this way, this side is not the same as this side. So you really cannot divide by 2 because it doesn't make any sense. This surface is something, and this surface is something completely different. So bad idea. So we struggled with this, and for gallium nitride. For some things you can utilize symmetry and build a polyhedron with equal facet, and then you can get around it. In some cases you cannot. I was dealing with this, and then I was pretty much fortunate because we wasted a lot of time over the way around it. I had a chance to talk to John Kahn. There was a workshop in Minnesota, actually. It was DARPA workshop of applied mathematics. And John, in his late years, became very much into mathematical issues. So I had a chance to talk to him, and John listened to me and said, oh yeah, of course, just give up. Stop working on it, there is no surface energy, you cannot use roof construction, and all you have to do, you should read my old paper. And this paper will not help you, but it will explain that you should give up. Okay, so, but he also pointed to other people's paper, which just preceded. They published it back to back. It's not very visible journal. This is by Lee Aronson Russell, LAR. What happens there? They publish this kind of strange thing that if you add this function to surface energy, which is initially isotropic here, right? And you add this function, and you do same minimization of energy of the whole surface. It has this fancy name, Limacon de Pascal, which is kind of snail. It's a well-known curve. You get again sphere, which means that you change energy of the surface energy in all directions. You changed it a lot in some arbitrary fashion because A and B are arbitrary, but you get the same shape. So this was obviously for John, it was a push, and then they published pretty extensive study where they demonstrated that there is this gauge invariance that you really can, for certain symmetries, I'm not going to discuss the math of it because it's pretty heavy study, but I quote here, literally copied, not to distort the message, conclusions from their work. This arbitrary addition has no effect on any measurable property, which means that it really doesn't have any physical sense, the absolute value of surface energy, for some symmetries. Then they identified 10-point group symmetries for which it's really true. Surface energy surprise doesn't make any sense. Absolute value can never be made, neither experimentally or calculations theoretically, and that's just reality. Interestingly, what is it? It's 15 years later, he published again. He obviously heard a lot from colleagues who were very unhappy with this situation because it's unusual that he put this sentence in the research paper. He says, for those who are very uncomfortable with this, there is a small consolation. Yes, there are some symmetries where surfaces can be worked out, but sorry about it. In some cases, it just doesn't make any sense. So, and the list of symmetries here, we don't need to worry about technical detail. So this gamma surface energy can never be known in principle, unless symmetry is high enough to make it definable. It's just undefinable. And I was kind of, okay, we stopped this effort at that time to find this good side representative, but it's a very bothering statement if you think about it. Because nature somehow finds equilibrium shape. So it means that full construction with an existing form just fails, and it's a challenge for theory. What do you do? What do you do? Of course, equilibrium shape still exists, but surface energy doesn't. So this was a while ago. So when we started with this team with the mentioned, the obviously was that the irony of this full construction of theory is that it gives you a recipe how to find the shape, but it doesn't tell you where to get the input, where to get surface energy. This is number one. And then things became even worse over years when come to basically that you cannot get surface energy. It just doesn't exist. And then you're stuck in this situation, which is bizarre because again, natural shapes do form. So we started looking at it. And of course, I will go quickly through obvious things. In case of graphene, again, I repeat, graphene is an iconic material for 2D. Now I'm in 2D because it's easier. Graphene has inversion symmetry. So you compute this, subtract, divide by 2, you get this. Armchair side, you get this. And then you can predict shapes, and this is done, and this was nice, and people liked it. You can predict shape, no problem. It has really nothing to do with the topic of today. Then you go a little bit one step harder, is boron nitrogen. With boron nitrogen, this trick doesn't work, right? I don't know, I can use my hand, or I can use fancy laser point here. You see, for armchair edge, you can divide by 2 and get edge energy. But for zigzag edge, you have boron on one side and nitrogen on another side. So you cannot divide by 2, and you're what? To my surprise, were about 10 people published about this ribbon using average value, but average value just divide by 2 anyway. But of course, average value doesn't make any physical sense because they're completely distinguishable objects. One is nitrogen, another is boron. If they have energy, it's its own energy. So we worked it out. We worked it out in this case by resorting to polygons. Luckily, boron nitrogen has trigonal symmetry. So you can design polygons so that each case, as you see, will be fully boron or fully nitrogen. And then you can divide by 3. And then you have from 3. You can design, then you can do energy defined well for each side. For each side. Oh, then I have nothing to say. Okay, so boron nitrogen can be done. Let's go to the quantum properties, which I will skip. This is boron nitrogen inclusions depending on chemical potentials in carbon or carbon in the end. And then we come to problem which was not solved. You have crystals of symmetry where you cannot do any polygon. You cannot do any polygon whatsoever. And the Gedanken kind of crystal can be just this. If you don't want to worry about atomistic details because some of them are complicated, you look at this. This is Y crystal, lowercase y. It has no symmetry whatsoever. It is C1. So no matter how you cut it, all edges will be not paired and no triangles, nothing. You never have kind of complete set to solve it. So what do? This is a little bit better. You can see that 2 and 2 can be resolved because you can have a slab, but anything else you cannot resolve. So what do? For Wolf construction, this continuum function. This is pretty easy, and maybe we'll skip with this we did long ago. You can, for arbitrary cut, you can just write energy, you can decompose it into this and this, as you see from DFT calculation. Really, this cut looks like some of them like armchair, and some of them are zigzag. So you can write algebraic equation and then transform it into trigonometric. Important thing, you get continuum function for any angle you have. But of course, you need to provide basic basic energies is very definable. So then you go to low symmetry. To low symmetry, what do you do here? You design several equations where you know total energy. So you have 2 is the only one definable because it is symmetric. 2 here and 2 here, you cut a slab, you divide by 2, you have energy. It's right here in the middle. All others, as you see, are not definable, and you have total 1, 2, 3, 4 equations, but you have 5 variables. So you have underdetermined system which you can never solve. And this was kind of a problem. What do you do? I don't know, okay, what the hell? It's like a Columbus egg. You just do something strange. You break egg and it stands, right? So in this case, I thought we will just add some equation, any equation pretty much. For example, this one. And this alpha on the right-hand side doesn't matter, whatever, arbitrary auxiliary equation, we call it. It's kind of latent surface energy because it really doesn't. And then you see what happens. And then we can solve it for any alpha. And then, of course, what happens is interesting because when you solve it for different alphas, you see that gamma plot, this thing is called gamma plot. Energy is a function of energy. Gamma plot changes, but your equilibrium shape is invariant. Equilibrium shape is shifted, and you're done. So you can't do it, right? So you can't do it. And then we go to real material. That's a bit heavy, but you gave me 5 minutes. Real material, that's where a lot of work is, always doesn't add anything in principle. If you go to example of thin selenide, which is popular because it's extraordinary good thermoelectric, just side comment. You set up these equations 1, 2, 3, 4, 5. 1, 2, 3, 4. 5 is a fake equation, remarkably. These are from values are all from density functional calculations or anything you want. You can do precise, not precise. The principle is important. You set up these equations. These are total energies on the right-hand side. Because you have multi-component material, there is of course chemical potential, which is a real thing. It can change the shape. So you have 5 equations, you solve them, and you have different shapes independent on your latent energy alpha. Invariant, but they do change with chemical potential. That's reality. So if you change chemical potential balance between these 2 elements, you go through this thing, and you can predict possibility of different shapes, and they're observed as you see in experiments, and now we understand why. Why I don't go to this one. The last one is the most asymmetric. This one is interesting because none of values for edge energy in this polygon is definable or known as it cannot be known. Nevertheless, you can again, following this idea, you can set up equations. 1, 2, 3, 4, 6 are real, but you have 8 unknowns. So you add these 2. These numbers do not matter. I only list them because that's how plot is plotted. But they do not matter because it's only shifts. And you can see the result is that it shifts, but you have real shape, well-defined physical thing. When you don't have any information, well, you have some, of course, algebra existing works. We applied it to this material, which is silver nitride. And as you see, it beautifully produces. First, when you produce shape like this in calculations, you think something is wrong because it's some needle with a slanted cut. I couldn't believe it. Then it took us a while. This shape, this is actually shape, this black part. This is zoomed. It's completely asymmetric, and I think cannot be. It's a bizarre shape. Then we found experiments where this needle really have similar angles and similar dimensions. So this is pretty much what I wanted to say. You don't need to know this algorithmic part. How to circumvent these unknowns. It just reminds me of this modern philosopher If you allow me to quote Donald Rumsfeld, so sometimes you can find a way to go around it and really find the important physical properties. And that's just one. This is also example of this low symmetry crystal, real crystal. So thank you very much.